This is part 2 in our series of lectures on proofs of theorems on finite sets. In this lecture, I'm going to talk about the cardinality of finite sets. Remember that in the previous lecture, we proved the Pigeonhole Principle, which says that given any pair of natural numbers m and n, if m is bigger than n, then there does not exist an injection from n sub m to n sub n. So in this lecture, we're going to prove an analogous result which concerns surjections. Here's the result we're going to prove. For all m and n in the natural numbers, if m is smaller than n, then there does not exist a surjection from n sub m to n sub n. So we're going to prove this result using principle of mathematical induction, but we're going to do the induction on the m rather than on the n. So this is just a reminder of what it is we're trying to prove, and I say that we're going to do it by induction on m rather than on n. So why don't you see if you can write down what is the set S which we should be looking at, for which we want to prove that S is equal to the set of all natural numbers. Well, I said that I was doing the induction on m, so that means we should take S to be the set of all m, such that the remaining part of this statement is true for every n in the natural numbers. So in other words, it's the set of all m, such that for all natural numbers n, if n is bigger than m, then there does not exist a surjection from n sub m to n sub m to n sub n. So the first step in the proof is to show the basis step that 1 is an element of S. So in other words, we need to show that for all natural numbers n, if n is bigger than 1, then there's no surjection from n sub 1 to n sub n. See if you can write down the proof of that. So here's my proof of the basis step. We first show that 1 is an element of S. So that means we have to give ourselves an n in the natural numbers, and we have to assume that n is bigger than 1, and we have to deduce that there's no surjection from n sub 1 to n sub n. So what I do is, so I say let n be an n, suppose n is bigger than 1, and now I just simply give myself a function from n sub 1 to n sub n, and I just have to verify that it can't possibly be a surjection. Well, n sub 1 just consists of a single element 1, and so the range of this function is just simply the singleton set f of 1. It can only have one element in it, and since n is at least 2, n sub n has more than one element in it, and so it's impossible for this range to agree with n sub n, and that's another way of saying that f is not surjective. So that completes the proof that 1 is an element of S. Now the inductive step, just as for the Pigeonhole Principle, I'm going to do it using the method of contradiction. So see if you can write down the first few lines of the proof of the inductive step if we're assuming that we're going to do it using the method of contradiction. So here's the beginning of my proof of the inductive step. I say let m be a natural number, suppose m is in S. We have to show that m plus 1 is in S. We argue by contradiction. So that means I'm going to assume that the negation of this statement is true relative to m plus 1. Okay, so that would say that there exists a natural number n such that n is bigger than m plus 1, and there does exist a surjection from n sub m plus 1 to n sub n. And that's, I believe, what I wrote here. Then there exists a natural number n such that m plus 1 is smaller than n, and there exists a surjection f from n sub m plus 1 to n sub n. Now the idea is, it's going to turn out to be fairly easy to finish the proof if f maps m plus 1 to n. So I'm going to consider separately the case where f of m plus 1 is n, and f of m plus 1 is smaller than n. So here's the proof of case 1. If f of n plus 1 is actually equal to n, then I'm going to consider the restriction of f to n sub m. Now, if there happens to be some element other than m plus 1 which maps to n, then the restriction of f to n sub m is going to be a surjection from n sub m to n sub n. In other words, we didn't really need the m plus 1 to get n in the range of f, because there's some other element other than n plus 1 which is mapping to it. But on the other hand, if n plus 1 is the only element which f maps to n, then the restriction of f to n sub m is going to be a surjection, but it's going to map into n sub n plus 1, because there won't be anything in here that maps to n minus to n. So in either case, we obtain a surjection from n sub m into either n sub n or n sub n minus 1. But our assumption is that n plus 1 is smaller than n, right, because we wrote that here. And that means m is certainly smaller than n and also smaller than n minus 1. So that gives us a contradiction to our assumption that m is an element of S. So that completes the proof of case 1. Now the idea of case 2 is to somehow use this f to produce a new surjection from n sub m plus 1 into n sub n in such a way that m plus 1 maps to n. Okay, if f of m plus 1 is smaller than n, then that doesn't happen. So we want to come up with a new surjection. We're going to use f to produce a new surjection from n sub m plus 1 to n sub m n, such that m plus 1 does map to n. So see if you can figure out how to do that, and I'll show you my solution in a few seconds. So here's my proof of case 2. Suppose f of n plus 1 is smaller than n. Well, since f is surjective, there has to be something that maps to n, so that means there has to be a k somewhere in this set here that maps to n, but k is not n plus 1, and so it must lie in n sub m. So now what I'm going to do is I'm going to introduce this function g that's going to take all the elements of n sub m plus 1, and it's going to interchange two of them. It's going to leave all of the elements alone except for k and m plus 1, and it's going to interchange those two. So here you see the definition. G of x is equal to x if x is neither m plus 1 nor k, but if x is m plus 1, I'm going to map it to k, and if x is k, I'm going to map it to m plus 1. So essentially G is taking the elements of this set, and it's just simply interchanging two of them. It's interchanging m plus 1 and k. Now look what happens. Of course, this G is a bijection. So when we compose G with f, we get a surjection, still from nm plus 1 to nn, but I claim this time m plus 1 is now mapping to n, because G takes m plus 1 to k, and then f takes k to n. Okay, so that gives us a surjection of these two sets, which maps m plus 1 to n. And so we're back in case 1, right? We showed in case 1 that the assumption that there was such a surjection leads to a contradiction. And so we obtain a contradiction in case 2 as well as case 1. And so that completes the proof of the inductive step. And therefore it completes the proof of the theorem. Now it's a really simple matter for us to prove this theorem. If x is any finite set, then there exists a unique natural number n and a bijection from n sub n to x. So what is this theorem really saying? Well, the fact that x is a finite set, all that tells us is that there exists an n and a bijection like this, but it doesn't tell us that it's a unique n. Okay, so the theorem is asserting that the n that we get from the definition of finite set is unique. So let's see if we can prove that. So by definition, there definitely exists in N and a bijection from n sub n to x. But suppose there's some other natural number, say m, and some other bijection, g, that maps n sub m to x. We have to convince ourselves that m and n are the same. Now, since f is a bijection, whenever you have a bijection, it's always true that f inverse is also a bijection. It's going to go the opposite way. It's going to be a bijection from x to f sub n. Now we take the composition g composed with f inverse. That's going to be a bijection from n sub m into n sub n. Now the pigeonhole principle guarantees that this is an injection, and therefore m has to be less than or equal to n. But the theorem on surjectivity that we proved earlier in this lecture says we have a surjection from n sub m to n sub n, therefore m must be bigger than or equal to n. Okay, so those two inequalities tell us that m equals n, and that completes the proof. That proves the uniqueness that we're looking for. So finally, we're able to define what we mean by the cardinality of a finite set. If x is a finite set, then there exists a unique natural number n and a bijection f from n sub n into x, and this unique number n is referred to as the cardinality of x. Of course, there's nothing startling or surprising about this definition, but you'll notice that we had to do quite a bit of work in order to be able to make this definition.